The life cycle of a star. The star cycle, or life cycle of a star, refers to the different stages a star goes through during its existence. Our story begins in the nebula. The nebula is a giant molecular cloud. Actually, they are massive clouds of dust, hydrogen, helium gas, and plasma. More importantly, they are stellar nurseries, or the place where stars are born. It is important to note that the term nebula means a cloud in space. And this is important because within the nebula, there is what is called an interstellar cloud or interstellar nebula. The life of a star actually starts out as a cold and dense interstellar cloud. This cloud needs to be dense enough and cold enough so that gravity will overcome pressure. Interstellar clouds are made up of mostly hydrogen and helium, with heavy elements present in significantly smaller amounts. When the interstellar cloud becomes dense enough so that light cannot escape directly from its interior, but rather has to scatter or bounce its way out, the interstellar cloud becomes a protostar. When the collapsing interstellar cloud becomes a protostar, it will tend to heat up faster as it continues collapsing, since energy can only be radiated away at its surface. Due to conservation of angular momentum, a spinning disk of gas and dust will be formed around the protostar. This spinning disk, in turn, could give birth to planets. When the core of the protostar reaches sufficiently high temperatures to initiate the nuclear fusion of hydrogen to helium, it becomes a star. At this point, it is important to note that there is also one other option. If a protostar does not have sufficient enough mass to generate high enough temperatures to initiate the nuclear fusion, the protostar will become a brown dwarf, or what is called a failed star. That is, since the brown dwarf does not generate energy through nuclear fusion, it is not a star at all. Next, we must consider fusion. Fusion occurs in the core of stars and is reached when the density and temperatures are high enough. There are actually different fusion cycles that occur in different phases of the life of a star. These different cycles make the different elements we all know. The first fusion cycle is the fusion of hydrogen into helium. This is the stage that our own sun is in. In stars with a very high temperature, there are other fusion cycles that take place. At higher temperatures, helium burning produces carbon. Finally, at higher temperatures, the heavier elements like iron are formed. The fusion reactions occurring in stars makes neutrinos that reach Earth. By detecting these neutrinos, scientists learn about fusion inside the stars. Fusion actually begins in the protostar stage. When the core of a protostar becomes hot enough to initiate nuclear fusion of hydrogen to helium, that is when it becomes a star. A star at this stage is often called a main sequence star. However, there are several stellar life cycles that a star can follow at this point, depending on the mass of the star. Stars typically fall into two different types depending on those masses: low-mass stars or high-mass stars. Each type in turn presents different evolutionary stages after the main sequence stage. A low-mass star is a star of about 2 sun mass or less. Nuclear fusion of hydrogen into helium in its core occurs in a low-mass star through the proton-proton chain, just as in our sun. Our sun is in the main sequence and is known as a yellow dwarf star. Yellow dwarf stars are relatively small and contain between 80% and 100% the mass of our sun. So our sun is at the higher end of this group. Stars in this classification have a surface temperature between 5,300 and 6,000 Kelvin and fuse hydrogen into helium to generate their light. They generally last for 10 billion years. The core contracts and grows hotter until its energy output overcomes the star's own gravity. At this time, the yellow dwarf begins to expand and leaves the main sequence, becoming a red giant. In this stage, nuclear fusion is not occurring in the low-mass star's core, but occurs in a hydrogen shell around the helium core. The total luminosity of the star increases. That is, the energy rate production of the hydrogen-burning shell is higher than that of the hydrogen-burning core when the star was in the main sequence. The radius of the photosphere increases as well. However, the surface temperature decreases. Thus, the star goes towards the color red. Note that in the red giant stage, the luminosity increases even though the surface temperature decreases. Then, when the core of a red giant becomes hot enough to burn helium, the star leaves the red giant stage and enters the planetary nebula. A low-mass star does not have sufficient mass to generate the temperature necessary to burn carbon. When the carbon core of the star stops shrinking due to degeneracy pressure, energy sources for the star will have been consumed, and the star will begin to eject or blow away its outer layers. This is the stage where the outer layers of the low-mass star are ejected, and is called the planetary nebula. The name of the stage comes from the fact that the outer layers of the star begin to form a cloud that looks like a planet with the hot core at the center. The outer layers ejected from the star will continue moving outwards until eventually they become part of the interstellar medium. Once the ejected outer layers of the low-mass star become part of the interstellar medium, its hot core is left behind, and the low-mass star has entered into the white dwarf stage. A white dwarf star is thus the leftover core of a low-mass star. A white dwarf star is similar to a brown dwarf star, and the white dwarf star emits radiation as it's cooling down. When a white dwarf cools down to the point where it no longer emits significant amount of light, it is often called a black dwarf. A black dwarf star is sometimes called a dead star. A black dwarf is actually a white dwarf that has cooled down to the temperature of the cosmic microwave background, and, in other words, is invisible. Unlike red dwarfs or brown dwarfs and white dwarfs, black dwarfs are entirely hypothetical and cannot be proven to exist. Now, whether or not a black dwarf exists, and whether or not a white dwarf can evolve into a black dwarf is not for us to decide today. What we should talk about is that white dwarfs can become supernova, or more specifically, supernova type 1a. Supernova type 1a occur only in binary systems. That is when two stars are orbiting one another, and in which one of the stars is a white dwarf, while the other one can vary from a giant star to an even smaller white dwarf. The white dwarf is the remnant of the star that has completed its normal life cycle and has ceased nuclear fusion. It is important not to confuse type 1 supernova with type 2 supernova. Type 1 supernova, which we are discussing now, involve an explosion which results from sudden fusion on the surface. In type 1 supernova, the star is totally destroyed and the mass and brightness are consistent. Type 1 supernova occur in a stellar remnant, or the white dwarf, which we previously discussed. And last but not least, type 1 supernova do not have hydrogen lines in their spectrum.